All right, we're going to finish up section 6 of chapter 2. We finish up the limits involving infinity and asymptotes. Last time we talked about horizontal asymptotes. And we introduced the concept of, at one point, the vertical asymptotes, which we're going to cover in depth here today. But again, as you see, we can do it using calculus, or you can also do the work using algebraic observation. So, but we're looking at, more so, we're looking at limits as x goes to infinity, or limits as the function goes to infinity. That's what we're doing here. That's what we're looking at, limits of functions or infinity. We're looking at either x goes to infinity or the function goes to infinity as x goes to some number. So precise definition of infinite limits. The first one, for any function f of x, as the function goes to infinity, as x goes to c, we represent it this way. The limit as x approaches c of some function equals infinity. If for every value b that's greater than 0, there exists a delta greater than 0, such that the function is greater than that value b, in other words, it's positive, whenever the delta function stays the same, the 0 less than the absolute value of x minus c is less than delta. Remember what this symbol means? For every. This one means for every. This one means there exists. Because if you're going to study mathematics, higher level maths, you get to university, they're going to be using these symbols all over the place in lectures and stuff. So might as well get introduced them now. ST means such that. That means such that. I love the way the book put it. Instead of f of x lying arbitrarily close to some limit, as x approaches c, for all sufficient x's close to c, the definition of infinite limits is just the opposite. Is f of x has to be arbitrarily far from the limit to exist. We used to talk about as delta gets close to c, as x goes to c, f of x gets closer to L, gets arbitrarily, infinitely close. That's what we used to. Now in infinity, we're saying as x approaches some value, the function goes exponentially far away from that value. So it goes to infinity. So it goes very arbitrarily far away from 0. As far as away from 0 as you can get. That's what this is saying. As f of x goes to infinity, if f of x goes to infinity, as x approaches some value c, which is written this way, the limit of our function as x approaches c goes to infinity, if for every value b that's positive, there exists a delta greater than 0 such that this function is bigger than that. So in other words, this function is positive whenever x minus c is less than some delta, but it's also positive. That was with the positive side. Now for the negative side is if the function f of x approaches a negative infinity as x approaches c, written this way, limit of f of x as x approaches c equals negative infinity. If for every negative b less than 0, there exists a delta greater than 0 such that f of x is less than negative b whenever that same condition exists with the x. So here are the big things. F of X is going to be greater than B whenever X goes to positive infinity. And here F of X would be less than negative B when X goes to negative infinity. Let's look at example 15. We'll use these two definitions in example 15. Prove the limit as X approaches 0 of 1 over X squared equals infinity. So the first thing we have to do is we know we have a B that's greater than 0, not a B, a delta. Well, delta and B, must say both of them are greater than 0. Because remember, delta is how far the X value is from the C value. As X gets closer to C, that distance gets smaller, but it's still positive. Okay, so as this is true, we have X minus C is less than delta. This implies that our function is greater than B. So let's put numbers in there. X minus 0 is less than delta, implies our function 1 over X squared is bigger than B. Then we know that this is true if and only if the reciprocal is true. And this can be rewritten. Remember, we want the X value. So if we square root both sides, we get the absolute value of X is less than square root of 1 over B. The reason why we have absolute value is because, remember, all our values have to be positive. So it's 1 over square root of B. Because remember, what is B? B is larger than our function. B is also greater than 0. So it's a positive value. So what does this tell us? Now, now we got to make these. How do we relate both of these? Because what does this side equal? This is 0. Absolute value of X is less than delta. we have this and we have this. So what does that mean delta is? Delta is equal to 1 over radical B, right? So that tells us that our absolute value of x is less than delta is less than that. So as we started off, we have this, and that we know is less than, from here, we know 1 over x squared is greater than b. So what is b? Using this, we reciprocate those, we get 1 over and square both sides. So this is 1 over delta squared, which is bigger than b. Since b is a number greater than 0 and this is bigger, so as x goes to 0, this number it goes to infinity, which is what we're trying to prove. Because b is a positive number and b is less than this. So for any value b I pick, this number is always going to be greater. So I can pick a value b, as long as it's greater than 0, I can pick a billion. This number is going to be bigger than a billion. So where does it go to? It goes to infinity. So I can make b as large as I want to. So that's what I'm trying to prove. Because no matter what value b I pick, this number is going to be always larger than b. And if I pick b to be, let's say any value, this one's always bigger, so it has to be a larger value. So as this one goes to infinity, this one goes to infinity. All right. We talked about horizontal asymptotes and oblique asymptotes last time. How do we determine those? How do we determine horizontal asymptotes?
The numerator is less than the denominator, then that's the zero. But if it's equal,
No. No. You just said if the numerator is bigger than the denominator. It's not numerator and denominator, it's something else, something specific about the numerator and denominator. The what? Factoring? No. Horizontal asymptotes deal with the degrees. The degree of the numerator, the degree of the denominator. If n is bigger than m, it's the degree. If the degree of the numerator is bigger than the degree of the bottom, then the horizontal asymptote does not exist. It goes to infinity. If the degree of the numerator equals the degree of the bottom, then the horizontal asymptote is the coefficient, or is the coefficient of numerator and denominator. If the degree of the numerator is less than the degree of the denominator, then it's the x-axis. the exception to the rule, this one, except if n is bigger than m, if n is bigger than m by 1. Then we have an oblique asymptote. How do you find the oblique asymptote? Just tell me how to find it. Yeah. By long division. And remove the remainder. That's only for the oblique asymptote, because we're gonna look at another application of long division where we keep the solution part and we keep the remainder part, because both of those have places to play a dominant role in what happens to the function. So that's oblique asymptote and that's horizontal asymptote. Now we're going to look at vertical asymptotes. So what do you think a vertical asymptote is?
Along the x-axis?
Yes, the vertical asymptote, it's only going to cross the x-axis, but what exactly is it going to entail? What value of the x-axis? You only have vertical asymptotes when you have rational functions. Wherever the denominators equal 0, those are your vertical asymptotes. So looking at this example, do we have an oblique asymptote, a horizontal asymptote, or a vertical asymptote, or a combination of them? Now just look at this one. Well, we can only have one or the other. You cannot have them both for the horizontal and oblique. What determines an oblique asymptote?
+1.
Yeah, if the degree of the top is bigger than the degree of the bottom by 1. Is that true here? No. So it's not an oblique because the x exponent here is 0. There is no x value. So we have a horizontal asymptote. There are more x's on the bottom. So where's the horizontal asymptote? If there's more x's on the bottom than the top, then it's the x-axis. Vertical asymptote, where the bottom equals 0. So x squared plus 3x equals 0. Factor out an x. Set them both equal to 0. Those are your vertical asymptotes. These are lines that the graph cannot cross. Unlike horizontal asymptotes, where if you had a horizontal asymptote, well, we do, we have a horizontal asymptote here. The graph can cross the horizontal asymptote, but when it does, it has to taper off and get to the asymptote. So horizontal asymptotes can be crossed, but they have to go back down. The graph has to go back down to that asymptote. But vertical asymptotes cannot be crossed because that's where the function becomes undefined. So what happens at vertical asymptotes? Let's look at a definition. A line x equals a is a vertical asymptote if either the limit as x approaches some number a from the right equals plus or minus infinity, or limit as x approaches a from the left of that function equals plus or minus infinity. The most common cases in point here is that function. Yes, we've looked at this. Is if x goes to infinity, where does this function go? No. As x goes to infinity, what's the limit of this function?
0?
0. It helps if you look at the graph. The graph of this function looks like this. As x goes to infinity, it keeps on going forever and lower and lower and lower. It's approaching 0. But now, since we have a rational equation, let's look at where it becomes a problem when it goes to 0. Let's go to 0 from the right. And then we'll look at 0 from the left. As x approaches 0 from the right, where is the function going?
Say that again?
As x approaches 0 from the right, where's the limit of the function going? Here's the function.
Let's go into infinity.
It's going to infinity. Yeah, it keeps on going forever. It goes to positive infinity. The limits, okay, remember the limit as x approaches c of f of x equals L. These are the y-axis. These are the x-axis. So what number is this? Where is this function going? What y value is it approaching? The limits are always the y values. It's always. Now, as we come from the left, as x goes to 0 from the left, where is the function going? Negative infinity. Right. So that's what the definition tells us about vertical asymptotes. Vertical asymptotes are where the function, actually, the limit of that function goes to positive or negative infinity as x approaches some value.
Is there a point where we count it as meeting zero for things like tolerances or no?
Well, we can't, because in this case, if we actually get to 0, then it's undefined. Because 1 over 0 is infinity. 0 goes into 1 infinite number of times. So no, in vertical asymptotes, we'll never get to it. Because infinity is not a number. That's why I say it doesn't exist. We can say it approaches infinity, but it doesn't exist. Yeah, and that's where it gets kind of confusing, more of a philosophical concept. Right. So here's our function. Find the horizontal and vertical asymptotes of the curve. Yeah, because as we said, the degrees of both the numerator and the denominator are the same. Then it's the coefficients. So the horizontal asymptote is 1. The vertical asymptote is where the bottom is equal to 0. Okay. This one is y equals 1. That's not wrong, but it's not calculus. These are absolutely right, because that's all the computer will take is the right answers. So no problem. Let me show you how we would do it in calculus. First, let's do long division. Because remember I told you we're in the near future, we're going to use both the number and the remainder. That's what we're going to do here. So what times x gives me x? 1. So 1 times x is x. 1 times 2 is 2. Change the signs and subtract. So x plus 3 over x plus 2 becomes 1 plus 1 over x plus 2. This part is your horizontal asymptote. This part is your vertical asymptote.
So the remainder becomes our numerator?
Well, yeah, I'll show you why. Because for the horizontal asymptote, we have to take the limit as x goes to infinity. The limit of this function as x goes to infinity, this one goes to 0 because there's more x's on the bottom. So that's your horizontal asymptote. The vertical asymptote is we look at what value of x can we not use in our domain. We cannot use -2. So when x goes to -2, what happens to the function? There's 1 plus 1 over 0, which is 1 plus infinity, which is infinity. Which defines this as a vertical asymptote. Because as we go to -2, our value goes to infinity. Yeah, but as you can see, the algebra way is a lot faster. But this is mathematically how we prove horizontal and vertical asymptotes.
So for clarity, would we use y equals x equals, or would we use limit of x to infinity 1 plus 1 over x plus 2?
You'd use this way because we're going to use this later on, the same concept later on.
Okay.
But I'm glad you asked that. But you always have the algebra proof to fall back on. Because the answers have to be the same. Example 17. Find the horizontal and vertical asymptotes of this function. -8 over x squared minus 4. If you want to, you could do that. Ooh, we're getting close to the end. So remember, for the horizontal asymptotes, we're looking as x goes to plus and minus infinity. The vertical asymptote is where x approaches plus or minus 2, where you set the bottom equals 0. All right, let's look at this. The horizontal asymptotes. So we take the limit as x approaches infinity of -8 over x squared minus 4. So what happens there? Yeah, goes to 0. Because there are more x's on the bottom. The limit as x approaches -infinity. of -8 x squared minus 4. Because since this is an even function, if I put negative numbers in there and I square it, the bottom goes to infinity. 1 over anything over infinity is 0. So the horizontal asymptote is 0, or y equals 0. It's the x-axis. The vertical asymptote, as x approaches +2 from the left, of -8 x squared minus 4. What happens there? If you don't see it automatically, plug some numbers in. 0, 1. As it gets closer to 2, see what you get. Where's where's this approaching?
0.
No, it can't be 0. Well, yeah, because if you plug in 2 inside there, we get 0 on the bottom. So it goes to infinity. Do we go to positive infinity or negative infinity? Are you sure? That's what I said. Plug in some numbers. As we're getting closer to, we have -1, 0, 1, 1.5. We know the top is negative already. And if I take the bottom and I square it, so -1 squared is 1. 1 minus 4 is negative. 0 minus 4 is negative. So negative over negative cancel. 1 minus 4 is negative when negative cancels. 1.5. So as it gets closer to 2, is it going to positive or negative?
Positive.
It's going to positive infinity. Now, as x approaches 2 from the right,
Negative infinity.
right? Because now all these values here, 3 squared is minus 4 is going to be positive. So it's going to be negative infinity. Do we have anything else to check? Well, yeah, since our vertical asymptotes are plus or minus 2, because remember, we took this one, x squared minus 4 equals 0. So x is equal to plus or minus 2. We have 2 vertical asymptotes. Now we got to try as x approaches to -2 from the left. And then we got to do the limit as x approaches -2 from the right.
From the left.
Yeah, because the -3 squared is gonna be 9, so it's gonna be negative infinity from the left. And this one's gonna be positive infinity. Because if I'm going to the right, -2 from the right, I go from +1, 0, -1. So still, this is gonna give me a negative value. The top is negative. The question now. Let's look what this graph looks like. Since we know we have vertical asymptotes at -2 and 2. We have a horizontal asymptote at 0. Do we have any x-intercepts? The only way a fraction can have an x-intercept is if the top is 0. So we have no x-intercepts. What happens at 0? If x is 0, we have -8 over -4 makes it
It
when x
crosses
is
the 2.
0, makes it a +2. Remember, we have no x-intercepts. It has to be a continuous function. These are asymptotes. We know as we approach -2 from the left, where does it go? Positive infinity. As we approach 2 from the right, it goes to positive infinity. As we approach 2 from the right, it goes to negative infinity. As we approach -2 from the left, it goes to negative infinity. That tells us everything we need to know about the graph. This has to be a horizontal asymptote, so the graph has to get infinitely close to it. There is no crossing of the horizontal asymptotes, so no x-intercepts. So you see how the horizontal and vertical asymptotes help us to draw a picture? It tells us at +2. From the left, it goes to positive infinity. Can it be down here? Can it be below the x-axis going to the right? No, because if it was over here, then it'd have to cross the x-axis. So since that's our y-intercept, it has to keep on going higher from there. As we said, from x goes to -2 from the right, it goes to positive infinity. Example, that was number 17, number 18. The graph of the natural, okay, so we have our function is the ln x. The graph of the natural log function looks like this. Does it have a vertical asymptote?
Yes.
Yes. Y = 0. The y-axis. So the vertical asymptote is at x = 0. Why it's x. Does it have a horizontal asymptote? No, because the function still keeps on going forever. Does it have an oblique asymptote? Yes. Because remember, the ln function is the inverse of the exponential function. And that graph looks like this. About the line y equals x. All inverse functions are symmetric about the line y equals x. So the oblique asymptote is the line y equals x. So looking at this, as x goes to infinity, where does our function go? As x goes to infinity, where is our function going?
Infinity?
It's going to infinity. Because remember, we don't have a horizontal asymptote. In other words, when it goes to infinity, it either goes to 0 or infinity. So this one does, it just goes on forever and ever. Now we look at, can we go to negative infinity?
Yes.
No. Look at our graph. Can you use negative values in a logarithmic function?
Oh, I thought you meant along the y.
I know, trick question. So no, this one does not exist because our domain is only positive x's. So we can't do that. How about limit as x approaches 0 from the right? Because as we go to 0, now we're looking for a vertical asymptote. This one would be negative infinity because it keeps on going forever, ever down. Now how about that one? Does not exist. Because I can't use x's, I can't have a negative answer. Very good. Trick questions.
So we aren't using the inverse. We're just using the.
Well, no, it's just that since we're dealing with the ln function we know is an inverse of the exponentials. Because they're inverses, they have to be symmetric about the line y equals x. Because of that, it doesn't have a horizontal asymptote. It has an oblique asymptote. But it does have a vertical asymptote because it can't cross the y-axis. Example 19. The curves y equals secant x and y equals tangent x. We're looking for vertical asymptotes. For the trig functions, whenever you have a trig function, what's the first thing you want to do with them? We haven't done derivatives. Always put them in terms of sine and cosine. So secant is 1 over cosine. Tangent is sine x over cosine x. Because the vertical asymptotes are wherever the cosine x equals 0. Where do cosine x's equal 0? Plus or minus pi over 2. Three pi over 2 plus or minus. Plus or minus 5 pi over 2. Plus or minus n pi over 2, where n is an odd integer. If we look at the graph of the secant function, pi over 2, negative pi over 2. Pi over 2. Because we know we have asymptotes at all odd pi over 2 . What is let's look at the cosine function first. The cosine function looks like this. That's what the cosine function looks like. The secant function, because these are asymptotes, the lowest it can go is 1. At 0, remember this is 1 over cosine. At 0, cosine of 0 is 1. That's the lowest it can be. Because from here, everything else now has to, as cosine gets closer to pi over 2, what happens to the values? They go to positive infinity. As x goes to, in this case, as x goes to negative pi over 2, it goes to infinity. So these are our vertices. And it goes from there. That's the secant function. Because it all depends on the cosine value. The tangent function, again, has the same vertical asymptotes, but the difference here so it has vertical asymptotes at all the pi over 2's. At 0, sine is 0, cosine's 1. And you have asymptotes. As we get closer to pi over 2, this one goes to 0, that goes to 1. It goes to positive infinity, it goes to negative infinity. Positive infinity, negative infinity. Because it's periodic, once we find the first one, they all match that same from our midpoint. So as x approaches pi over 2 from the left, tangent goes to positive infinity. Why positive infinity? Is because they're both positive. And when you get to pi over 2, cosine becomes 0. So 1 over 0 is infinity. So it's positive infinity. As we go to negative pi over 2, again, once you get to negative pi over 2, that's 0, but the top is negative 1. So it goes to negative infinity. It goes to negative 1 over 0, which is negative infinity. So you have to understand what the graphs look like to figure these things out. That's the trig part of it. Now, dominant terms. The example we had earlier, which was the x plus 3 over x plus 2. When we did long division, that equation became this. The dominant term as x goes to positive or negative infinity of our equation, which part of this, or which term of this equation has the bigger influence? As x goes to infinity, this one goes to 0. So this part is the dominant term when we're going to infinity. As we go to negative 2, this one goes where?
To infinity?
to infinity. So now this is the dominant term. So whenever we go to positive negative infinity, the integer part, the horizontal asymptote part, is the dominant feature of the function. But as we go to wherever the vertical asymptote is, the denominator part has the dominant feature for it. So that's why whenever you have rational expressions, always do long division first, and then it'll give you the horizontal and the vertical asymptote parts, or the solution and the remainder. F of x equals 3x to the fourth minus 2x cubed plus 3x squared minus 5x plus 6. G of x equals 3x to the fourth. Show that although f and g are quite different for numerically small values of x, they behave similarly for very large values of x. Okay, so what they're saying is, as x approaches positive or negative infinity, f of x over g of x approaches 1. So how do we do that? Well, let's look at this. They're saying that as x becomes very large, the equations become very similar. So we take the limit as x approaches both positive and negative infinity of our f of x over g of x, limit as x approaches positive negative infinity of all that stuff. If x goes to infinity, what asymptote is that looking for?
A over B, 1.
Well, it's going to look for the horizontal asymptote. And since the degrees are the same, then we take the coefficients, 3 divided by 3. So that's what the question asks. As x gets infinitely large, goes to infinity, this ratio becomes 1. Because yeah, we could have done it algebraically, take each of these and divide it by 3x to the fourth. That'll give us 1 minus 2 over 3 over x. All these go to 0, but this is what it's talking about. Whenever you go to infinity, you're practically looking for the horizontal asymptote. If it was going to a value, then you're looking for the vertical asymptote.
So if we worked it out like we did yesterday, we'd still divide everything by the 3x to the fourth.
Right. Yeah, that's because that's the first thing you would have thought about doing. Let's divide it, but we're going to infinity. So yeah, what we would do is look at the coefficient, the degrees. We know that this and this are the same. The rest of them, since they're smaller, really don't do anything. Okay, that does it for chapter 2. Finally,
Would it make a difference if X was going to a different number?
yes, if it's going to a number, then we're looking for a vertical asymptote. Then we have to plug it in there. So for example, in this one, if we were looking for another one, if anything else that we look for, if it was for X going to 3, we'll just plug it in there.
Oh,
That's
we
not
just plug
too,
the 3 in and
yeah, put 3 in places of X and whatever it comes out with, that's your value. But the only place that we may have trouble with is at 0. Why? Yeah, because we have a 0 on the bottom. So now what we have to look at, we'd have to look at the limit of this function as it approaches 0 from both sides. So because again, if we're going to any number, if it makes the bottom equal 0, that's a vertical asymptote. Any other number is just a value. It's just a point on the graph. If it goes to infinity, you're looking for the horizontal asymptote, if it exists. All right, so that's it for chapter 2. It's finally done. That was a very long one, actually. That was a very, very long one. All right,